Now that we've learned so much about the general properties of linear systems of first-order differential equations, for example, which size the basis must have and so on, let's now turn to a system that we can actually explicitly solve. And in particular, what we now focus on is again a little bit more specific case, namely one where I have a linear system of differential equation with constant coefficients. That means that the matrix A that we have here in this equation is an n by n matrix, which does not depend on the time t, on the parameter t. It's just a constant n by n matrix. And what we'll do for this equation here is that we will solve it twice. First, we'll actually write down a formal solution, which is very elegant, but as you will see, is not so practical for writing down numbers. But it's very interesting, very useful for, or also comes back in quantum mechanics. So I think it's actually very useful to have a look at that. And then finally, I will actually show you how you can use the eigen decomposition, the eigenvectors and eigenvalues of this matrix A to solve that system of differential equations. But let's start with this formal solution. And for this formal solution, what we want to introduce is a so-called matrix exponential. So we want to define the exponential of a matrix as we write it down here. So how is this actually defined? We know exponential functions for real numbers. We know it for complex numbers. How does it actually work for a matrix? And well, essentially, it works similar to what we did for complex numbers, namely, one uses the Taylor expansion of the function, in this case, the exponential. And instead of a number x, you put in the Taylor expansion a matrix. And here we only have powers of a matrix, so multiplying matrix multiplication. So that is well defined. So we can indeed, with this expression here, define the matrix exponential. There is a thing that I have to warn you about when you see this matrix exponential, and that is that for matrices, the exponential function doesn't always behave like you know it from real or complex numbers. For example, when you have e to the power of x times e to the power of y, this is not always e to the power x plus y. It actually only is for matrices that commute. But we'll not go into these subtleties here, but it's always good to keep that in mind when you see the matrix exponential. So what I basically want to show you is that this matrix exponential that we have here, that one actually is the solution to our differential equation that we have here. And to this end, what do we need to do? We need to do an explicit calculation showing that this one here fulfills the differential equation. And that's what we're going to do now. So we're going to start, we need to take the derivative of e to the at with respect to t. And what I did here is I just plugged in the definition in terms of the Taylor series. And what we're going to do now is just apply this derivative to all the terms in the series. So here we get sum over n equals to, well, here in the series we have a term which is a constant, n equals to 0. So that one becomes 0 when we take the derivative. So the sum does not go from 0 to infinity, but from 1 to infinity. And we get a to the power of n times, well, we had t to the power of n here. That is, we take the derivative, so we just get t to the power of n minus 1 times n divided by n factor t. So, well, here I can take a and t to the power of n individually because t and a commute. T is just a number, so I can just pull that one out. Well, now I can simplify that because I can now rewrite this as n equals to sum over n equals to 1 to infinity of a times a to the power of n minus 1, t to the power of n minus 1 divided by n minus 1 factor t. So we divide numerator and denominator by n. And now what I can do is I can take that constant matrix out of the sum because that's in every term. So I get a times sum over n equals to 1 to infinity a times t to the power of n minus 1 divided by n minus 1 faculty. And what I can do now is I can just rename the index n here, and I define a new index n prime, which is the same as n minus 1. Then I need to always replace n minus 1 here with n prime. And then we see we actually got back our original definition of the matrix exponential. So we find that this one is simply a times e to the at. But what you now see is that e to the at, the time derivative of that, equals to a times e to the at. So it fulfills the differential equation. And in particular, what this means is that the columns of e to the at are a basis for the solutions of the differential equation. Now, it's clear, well, e to the at, that's an n by n matrix by definition. Now we know that in order to figure out that it's a basis, we need to show that the determinant of e to the at is not equal to 0, and it's enough if we show that for a single time t. So for example, we can choose time t equals to 0, then e to the at equals the unit matrix, and that obviously has determinant of a unit matrix not equals to 0. Quite general, you can actually show that this matrix here is invertible for every t, because the inverse is just e to the minus at. So from that perspective, also we know that all the columns of a of e to the at are linearly independent and form a basis. So with this, we can then also write down the solution for a specific initial condition, and we find the solution x of t equals e to the at times x0, where actually if I now put in x of 0, I have e to the a times 0 times x0, which is the unit matrix, which I denote as I here, times x0, which is simply x0. So what we have here is the solution to the initial condition x of 0 equals to x0. So with this, you see we have a closed form solution, and well, it's very elegant actually, right? Now the problem with it is that if you want to, solve this for a specific matrix, specific values of the matrix, it's not the most convenient to use this expression, because basically to compute it, either you have to go to numerics. It's actually possible. You can actually compute a matrix exponential numerically. But doing it by hand would be very inconvenient, because in this case, you would have to calculate that sum here, and it's an infinite sum. Well, it actually converges, but it's not what you want to do by hand, basically. So what I'm going to show you next is actually a more practical approach of solving a linear system of differential equations with constant coefficients, for which we will use the eigendecomposition of the matrix A. So for that, we actually have to distinguish a couple of cases. And I will start with the simple case, and that is the case 1, where A is diagonalizable. And what does that mean? Well, it means that I can write down the eigenequation A times eigenvector Vi equals lambda I times Vi, and I find n eigenvalues, and the vectors V1 to Vn, they form a basis of the n-dimensional vector space. Now, the matrices that you've been looking at in quantum mechanics, they're always Hermitian. These are always diagonalizable, but I will later show you an example of a matrix where this is actually not the case, where I actually cannot find enough eigenvectors such that they form a basis of the n-dimensional vector space. We will now use these eigenvalues and eigenvectors to make an ansatz for the solution of the linear system of differential equations. And the ansatz is written here. We say that phi I of t equals to the vector vi times ui of t, where the ui of t are some unknown function of t that we want to determine. Now, what do we have to do? Again, we want that these are solutions to the differential equation, so we just have to plug them in. So we have to compute vector phi I of t, the first derivative with respect to t. And well, for that, we just need to plug in this definition here, and we need to take the time derivative of vector vi times ui of t. And note that vi does not depend on the parameter t. So this was a constant with respect to that. So it's also very easy. So we just get the easy result that this is vi times ui dot of t. Now we want that this vector phi I fulfills the differential equation. So this needs to be equal to a times vi vector ui of t. So we're, just to remind you here, we just used that. We want that phi I dot of t equals to a phi I of t. Now, but because we had vi being the eigenvector of a, we can simplify this to give lambda I times vi ui of t. But now we see that here there is no matrix involved anymore. We have an equation where we have this vector here twice. For this equality to hold, the coefficients need to be the same, so that we can deduce that ui dot of t equals to lambda I ui of t. But now you see that's the differential equation we've solved several times now already in our simple examples. And we know that the solution is an exponential function, and we get ui of t equals to ci times e to the lambda I times t. So with all of that together, we can write down the general solution. Which is x of t equals c1 v1 e to the lambda 1 t plus up to cn vn e to the lambda n times t. Well, how do we actually know that this is a full basis of the solution space? Again, we need to check whether the determinant of the basis vectors is not equals to 0. And well, we know that determinant of v1, vn is not equal to 0 because that's what we assumed. And we assumed that the eigenvectors form a basis of the vector space, which, as I said, for emission operators, for example, they always do. So from that, we can deduce that this is indeed a basis. Just remember, so what I'm basically just doing here is I'm checking whether these vectors here for t equals to 0, where this part just drops out, just becomes a 1, whether the determinant for this is not equal to 0. And as I said before, it's enough to check that for one single time t0. So this means that if we can solve the eigenproblem, and we actually exercised it quite a lot in the last week, we have a solution to our linear system of differential equations. So let's do an explicit exercise. So what I want to solve is this problem here. I want to solve the problem x dot of t equals, well, this matrix 2 by 2 matrix, which is off diagonal minus 1, 1 times x of t for a specific initial condition that I specify here. So what we have to do is we first have to solve the eigenproblem. So we know that for finding the eigenproblem, we need to solve the equation determinant of, well, this matrix minus eigenvalue on the diagonal. So minus lambda, minus 1, 1 minus lambda, which is simply lambda squared. And then we get here a plus 1 from the off diagonal minus 1 times 1. That this has to be 0. And this means that our eigenvalues are lambda 1, 2 equals to plus minus I. Because the square of plus minus I is minus 1, and we have minus 1 plus 1 equals to 0. Now we also need to find the eigenvectors. For that, we basically need to write down the problem once more. We now need to write down 0, minus 1, 1, 0 times an eigenvector, say, which we parameterize with A and B, equals to, well, for the first angle, plus I times A, B. And from that, we can easily see that this is fulfilled if V1 equals to 1 minus I. So please sit down and just check what I'm calculating here, that this is indeed the true solution. If we do the same for the negative eigenvalue, we get 0, minus 1, 1, 0, AB equals to minus I, AB. And then we know that the second eigenvector is 1, I. Okay, now we have eigenvalues and eigenvectors. With that, we basically know already the basis vectors, which are, the first eigenvector times e to the lambda 1t, when lambda 1 was plus I. So we have e to the it here. The second eigenvector is 1i times e to the minus it, which is the second eigenvalue. Okay, now these are the basis vectors. Now we also need to choose the coefficients such that the initial conditions are fulfilled. We need to write down the initial condition explicitly. So we have C1 times phi 1 of 0 plus C2 times phi 2 of 0 equals to 1, 0. Or if we just plug in what we have here, it's C1 times 1 minus I plus C2 times 1I equals to 1, 0. Well, from this, we see that from this second row here, we can easily see that this is minus C1I plus C2I equals to 0, which means that we have minus I C1 plus I C2 equals 0, which immediately means that C1 equals to C2. And on the other hand, we have the first row, which says that C1 plus C2 must be equal to 1. But since they have to be the same, it means that C1 equals C2 equals 1/2. So with that, we can write down a general solution, and that is x of t equals to 1/2 e to the it plus e to the minus it. So this is the first row here. And then we have here 1/2 times minus I e to the it plus I e to the minus it, which is simply corresponding to this second row here. Now, if you look at this, of course, you see immediately that the upper result here is just the cosine. So it makes sense to have a closer look at the lower part here. And of course, also here you see that this is looks very much like the sine, and we can actually get the explicit expression if we divide by I. So if we bring I here into the denominator, so then the minus I here becomes a plus I in the denominator, and we get a minus sign here. And then you see immediately that this is just equals to cosine of t and sine of t. So what do we learn from this example? Well, we do see that how this works in practice. And we also observe something, namely that the final result is cosine and sine, which maybe you wouldn't have thought about when you just saw before that the basis solutions are all exponential functions. But this simply comes from the fact that if we have imaginary eigenvectors of this matrix, that we are considering matrix A, then we also get complex exponentials, and those give rise naturally to sines and cosines. So this is what we can expect as solutions for linear differential equations. of first order. Now, what we considered so far was case 1, where I said A is diagonalizable. Now I want to look at you with a special case. I want to restrict myself to a 2 by 2 matrix and a so-called defective matrix A. So for A defective, we have the situation that determinant A minus lambda has a root with multiplicity 2. So remember, for a 2 by 2 matrix, of course, we only can have 2 eigenvalues and 2 eigenvectors. Here we basically have a degenerate eigenvalue. It's you basically get a solution of a root with multiplicity 2, so just one eigenvalue. And we want to consider the case where there is indeed, for this one eigenvalue, only one eigenvector. You can also have the situation that there is a eigenvalue with a multiplicity 2, but you get 2 different eigenvectors. Then this just reduces to what we had before. Then these eigenvectors form a basis of the vector space. But this can actually also be different. For this, let's look at an example to see how this can come about. So here we look at the matrix A equals to 1, 1, 0, 1. So it looks relatively harmless, right? But now let's calculate the eigenvalues and eigenvectors. So what we get is that determinant of A minus lambda is 1 minus lambda, 1, 0, 1 minus lambda. And this is simply 1 minus lambda squared, because the 0 times 1, it's just 0. And this has to be 0. So we know that we have as our eigenvalues, we have lambda 1, 2 equals to 1. Okay, so there's just the eigenvalue 1. Okay, so let's now solve for the eigenvectors. We need to do 1, 1, 0, 1 times AB equals to 1 times AB. And that just gives us that A plus B equals to A and B equals to B. Now, the second equation, that's just trivial, of course, but the first equation tells us that B equals to 0. So if I now write down my eigenvector here, I see that I can only find one single eigenvector, because basically what I see here that A is free, but that's just just a scaling. So for example, now I just choose A equals to 1 and I just find the eigenvector 1, 0. And that one does not span the whole vector space, obviously, right? So the problem what we have here is that with the recipe that we had before, we only find a single solution. So with the single eigenvalue and eigenvector of our previous calculation, we can only formulate one basis vector, which is v1 times e to the lambda t. And but that's not enough for a basis, right? We need 2 solutions in the basis. So what is the second solution? And for this, we use an ansatz. We write phi 2 of t equals v1 times t times e to the lambda t. So we basically take our previous one and we introduce the parameter t here additionally, plus v2 times e to the lambda t. So you see this is a more complicated solution, and well, it's not totally obvious that this should be the solution. So people have figured this out in the past, and what we're going to do here is basically just check that we can indeed make this into a solution. And in order to do that, we need to see if we can make that ansatz obey the differential equation. So we need to do what we've been doing always this time. So we need to first take a derivative with respect to time. And well, the first term here has two terms which depend on t, so we need to use the product rule. And we get v1 times e to the lambda t, where, because d dt of t equals to 1. Then we need to take the derivative with respect to t of the exponential, so that just gives us a lambda. So we get plus lambda v1 t e to the lambda t. And for v2, we have just a single term that depends on t, that is v2 times lambda times e to the lambda t. And since this should fulfill the differential equation, this should be equals to a times phi 2 of t which plugging in the definition of the ansatz, we get A times V1 times T e to the lambda T plus A V2 e to the lambda T. But now we know that since V1 is an eigenvector, we know that this is equals to lambda V1, which means that this term and this term cancel with respect to each other. What you see now is that we have an expression with the known vector V1 and the unknown vector V2. And what you want to determine is basically this vector V2. And to this end, we just collect all the terms with V1 on one side and with V2 to the other side. And if we do that, we arrive at A minus lambda times the unit matrix times V2. So this is this term here and this term. So the exponential here, that cancels out so that I can remove from both sides of the equation, equals to V1. And that means we can find a solution if we can solve this equation. So this is again the general equation, you know. So let's just apply it now to the example that we just started in the previous slide. So I just repeated here what the general solution is. So the general solution is the one that we are familiar with already, just the eigenvector times e to the eigenvalue times t. And then the more special solution that we were writing down on the previous page, where the vector v2 obeys this equation here. And what we now need to do is find v2. And this we do by, well, writing down the equation explicitly. So we have a minus lambda. So remember, so a was 1, 1, 0, 1. And lambda was also 1. So actually I should be more precise here. I actually have lambda times the unit matrix. So what we need to do is we need to subtract lambda equals to 1 from the diagonal. So this is minus 1, minus 1. And well, that obviously you see we can simplify to 0, 0 times a b. So this is a parameterize our vector v2 equals to the vector v1, and that one was 1, 0. And well, now we actually immediately see that there is a simple solution for v2. So we can find that v2 equals to 0, 1 solves this equation, because, you know, if we do that multiplication, then, well, here you have just 0, so this automatically gives you 0, and here we get just b times 1 equals to 1. So this is the solution. Actually, it's important, so if you look at it, we might actually note there is more solutions possible, because this particular form of the matrix I can put in any value of a. And that's actually normal for that kind of situation, because what we have here is this expression a minus lambda, which has determinant equals to 0. So that's, you know, a matrix which is not invertible, which is a null space, and that null space is the other eigenvector v1. So basically, this vector v2 is only defined up to some multiples of v1. So there's different solutions possible, but in the end, this just means that your coefficients C1 and C2 will be slightly redefined. So with that, we can write down the solution, which is x of t equals to C1, 1, 0, e of t plus C2 times 1, 0 times t plus 0, 1 times e to t, where I just plugged in all the eigenvalues, the vectors, and lambda equals to 1 that we computed before. Now, this was a particular situation because this holds for 2 by 2 matrices, and basically what we did here generally holds when the multiplicity of the eigenvalue is 1 larger than the number of eigenvectors that you have. Now, you can also have a more general situation where the multiplicity is even bigger than 2. I will not do that case explicitly here. It's actually spelled out on the website so that you can see that how it works in general. It's something which we'll not ask you to do in the exam. Maybe for the experts amongst you, the more systematic way of doing this is actually to use another decomposition of the matrix A, which is the so-called Jordan normal form. That would actually allow for a very completely general way of writing down a solution for any arbitrary A. But to be honest, in practice, you usually encounter matrices which are either diagonalizable or at most have a deficiency of 1 or so.